So, good morning to everyone. Thank you for being here to the assessment of the sixth semester. This time we're going to have two teams. Each team is going to be presenting you for 15 minutes, and then we're going to be having 15-20 minutes of questions, depending on how many questions Cesar, Emilio, and Raul has. And well, first team, when you're ready, you can start.
Okay. Hello, good morning. We are team number one, and we are going to present lactic acid production and purification process through fermentation with lactic acid bacteria using stevia vangues as a substrate by Pamela de los Santos, Omar Zambrano, Mariana Gomez, and I, Javier Ramirez.
So, well, as an introduction, we have the Geo brand, which is a company located in Guatemala, specializes in creating natural sweeteners produced from stevia. Of course, this generates a waste of 1 tons wet bags per hour. So this stevia bagasse is main composition. It's dietary fiber and lignin, which can be used for further added value. So what can we do with these bagasse, right? We can use these bagasse, pretreated stevia bagasse, as a substrate for the production of lactic acid through the fermentation of lactic acid bacteria. So another of our project description is this, and the development of a purification process for the production of food grade lactic acid, and finally a technical economical evaluation strategy for the project in the Latin American market for lactic acid, specifically in the food industry.
We chose to do this process through batch culture because they yield higher concentrations of lactic acid compared to continuous cultures or fed batch. One of the biggest challenges in the lactic acid production is the price of the substrate, where using this stevia bagasse as represents a lower cost alternative.
Then we have our product description. We are looking for high purity products, that is 88%. We know that for preservation, we could use a particular fermentation foods. And also the property of the lactic acid is the pK at 3.86, is soluble in water, and also is high polar in hydroxyl and hydroxyl proof. Then we have our target market and plant capacity. We are looking like Geobrands is his capacity is 99.5 kilograms of lactic acid per year. Our market covers like 0.5 of the lactic from the LATAM demand, and it will be profitable up to 54.09. We choose this calculation by a margin we can increase or decrease the price for obtain the profit, and also made a wide market between or high scalable. Also, we have to take in consideration Colombia leads the Latin in food in price lactic acid and contributes the 50% of the region output. Yeah, I got that. Sorry, my bad. To go to the next, please. And our target market is currently LATAM. We're looking like the value of $161.8 million of dollars. Our growth rate is 4.8 annually. We project like 2030 will be like 2068.2 millions of dollars, and our global market is 6 billion by 2031, and we expect an annual growth of 70.4%. As I told, it was a production capacity of 998 and
Okay, now this here we have a table with the all available technologies that it could be used to optimize the process. As you can see, the ones that are in black, they are the ones that we are going to use. Also, okay, as you can see, the ones that we use, that all of them are associated with the literature, and these one are selected because in first step we thought it would be a good process for our process, and we also have the the press study of our lab practices.
So now here we have our bioprocess diagram and mass balance, and from 1.5 tons of virus that enter the system, we can produce lactic acid, well, 32.15 kilograms through this pretreatment train and in production and purification. So first we have the steam explosion and enzymatic hydrolysis, which are pretreatments, and then like the fermenter, centrifugation, then a series of filtrations, and finally it passes through an ion exchange chromatography, then to concentrate and nanofiltration, and then we have a product, and we have to highlight here that the ones that are in green are the processes that we escalated.
Next, we have the overall global mass balance table, where we can observe the pretreatment, which is the steam explosion hydrolysis and the enzymatic hydrolysis, as well as the rest of the normal process from the fermentation to nanofiltration, where we can observe the input and the output mass of each equipment.
And now we have a table with the purification and recovery. First, we calculate the concentration about the literature and our lab experiments. As you can see, we are having a more high concentration level, having a global concentration of 91. And also with the recovery sustained with the literature, we can see that we have a very good recovery at the beginning, but we have a poor recovery at the end. This is because the nanofiltration wastes a lot of lactic acid at the recovery, and at the final we have a 34 of the global. And of this last one, you can see the purification. It have a ready for 1 to 2, and it was calculated to see the the difference of the purification in every step.
Next, we have the 5 scaled up unit operations, where we begin with a steam explosion hydrolysis with conditions of a volume of 7,000 liters with stainless steel, with a material of stainless steel, a temperature of 121 Celsius degrees, a pressure of 103.4 kilopascals, and a process time of 5.52, considering a cooling process of 1.27 hours to a temperature of 50 Celsius degrees. Then we have the anaerobic fermentation, where we have conditions of 3.3 RPMs, a temperature of 34 Celsius degrees, time of 4.2 days, with a stirred tank bioreactor with a Russian impeller turbine and a material of stainless steel.
Next, we have the centrifugation unit with the conditions of 2,435 gravities, the temperature ambient, and the set time, and also like the size. and then our microfiltration unit, which is like the pore size is 11 micrometers, and the pressure like also set. Filtration area and temperature ambient, and it's like the membrane should be ceramic membrane.
And then we have the anion exchanger. We have for the corrosion the resin that we are used. It's a styrene divinyl benzene in gel form. The temperature of work is 25 Celsius degree. It's stainless steel columns. For the pH, the load is 5, and the model phase is also 5, and the search is 2. The coil volume is 60 liters, have an input of 52.66 kilograms, and an output of 30.03 kilograms. Also, it have a height of 1 meter and a diameter of 0.1 meter.
Next up, we have the process logistics, where the lactic acid production process will take 209.543 hours. In each slide, we can observe each operation and their sub-operations. Then in the next slide, in the next one, we can observe how much 3 lactic acid production batches will take, which is 26.44 days, meaning 41 batches per year. And finally, we have the equipment occupancy chart to know how much time each equipment will be used.
Then we have the safe quality environmental aspects. We have 3 different countries. We have the United States with the normative 21 CFR 184. It's a regulation of lactic acid used in food specific using purity and safety standards. Then we have the 110 that is in good manufacturing practice and hazard analysis in risk-based intervention controls. It's applicable to food production. Then we have the Mexican ones, that is the Normativa F 420, that it established the specific quality requirement of lactic acid, such as purity and composition parameters, including concentration, pH, color, odor, and acceptable levels of impurities. And for the last but not least, the Guatemala, we have the RTCE, is an extension of the Codex Norm 192 1995, that is provided description of the production and manufacturing requirements by HPLC. Then we have the economic evaluation. From this one, we have a capital investment of 195 and $328 that we are including all the our unit product, each one of our process, and then we have our potential funding sources. It is more like Gia Brands established a food company under the same name. It's an startup designed for rise, found, and function as talent startup. It's practical funding solution about its business and corporate partnership that it will be access for advanced laboratories, technical experience, establish a market network, and boost credibility, streamline regulatory approval process, and mildly financial risk. At least we have the economical scenario evaluation that we have a ROI, that is the return of investment of 99.87%. Our equilibrium point that is 568. Our BC ratio that is 1.88. And our MVP that is a negative 52.37. That it means like the project looks money based on the assumption. And we have our first year of cash flow of 3,600, 356.74. After that, we have our conclusions.
Overall, we concluded that it is possible to produce lactic acid from stevia bagasse fermentation with a concentration of 91%. 1.5 tons of bagasse produces 32.15 kilograms of lactic acid in 209.43 hours, which means 386 bottles of 250 milligrams each.
So the ELA yields could be optimized by trying other concentration methods, such as membrane osmosis or membrane distillations, with yield a lot more than nanofiltration.
Then we look for exploring partnerships, runs as a subsidies to support economic borders during the pro-commercial phase, and consider also economical and market conditions that may impact the financial performance.
And also we use the same equipment for filtration operation and change the membrane size coverage for microfiltration, ultrafiltration, and ultrafiltration. And at the end, we can invest in more equipment in order to prevent bottlenecks. And that's it. These are our references, and thank you very much. Questions?
Thank you, Team One. So now we're going to the questions section. I don't know, Raul, Cesar, Emilio, if you have any questions for the team or specifically for a team member.
Yeah, I have in the bioreactor process, can you please that no, the other one. The fermenter. No, yeah. This one, no, la otra. That one. How do you cool? How do you pass from 121 Celsius degrees to 50 degrees?
In each case, we used SuperPro to estimate how much time it would take, and we use glycol as a cooling agent in this process.
No,
Or
what do you use to cool?
glycol.
It's a interchange. It's a how air, water. What is the medium device, medium liquid, or the liquid solution do you use?
Glycol.
Or how? How do you cool it? Could you please explain?
Sorry, I'm not understanding the question.
¿Cómo lo enfrías?
Sí, con glycol.
It's not only that you're gonna mix the glycol with the liquid, you should use like an equipment. So do you use like a what kind of heat exchanger? What kind of that's the question.
Okay, I understand now. Thank you. Well, in this case, in the SuperPro, I think that it's going through I don't know how it's called, like where the current goes. It I don't know, it will be surrounded by the liquid.
So it's like a jacketed reactor, and you cool
Yes.
it the liquid in the jacket,
Yes, that's what I mean. Thank you.
okay, yeah. Here you need usually that. Okay, yeah. In some cases that it's when you will need to load for this temperature. Sometimes first you would use air cooling first in order to prevent the thermal shock. Because
Okay.
you put so for example, you can put a chiller. It's not economical, but cooling tower, for example, a cooling tower, but they consider that. Okay, thank you,
Thank you.
Marian. In the Could you put in the batch section in the Gantt, please? the next one, next one. Okay, here it's you say, guys, that you will be able to produce 41 batches per year, is correct?
Yes.
And what is your batch size?
The batch size is of like the total volume
Yeah,
or
Or the,
batch, yeah, for example, raw material,
oh,
bags.
can we go to the
it's one
last
per
balance?
1.5 tons of bagasse. We will be making around 30 kilograms of lactic acid.
So if you multiply 1.5 tons of bagasse for 41, it's almost, it's very, how to say, it's not all the production we have for bagasse. I think it's only 1 week or 2 weeks.
Yes, we will need to increase the size
Yeah,
plant to
yeah,
cover all.
yeah. So you need to recalculate that because it's very amount. It's just for the, I am 3 weeks of production, something like that. It's very
Okay.
short. So, or you need to increase the size of the equipment or doing whatever. So,
Um,
you know,
we made this because we chose to buy 3 bioreactors where we can use them simultaneously, and that's why there's only like 41 batches per year because we used 3 bioreactors. Um, what we can do is, of course, increase this volume, but it would also increase the, how can I say it, the risk of bottlenecks. So we would have to actually buy more bioreactors for this to happen, or make a continuous fermentation. But it's not, as I said in the justification, it's not as achievable to obtain this quantity of lactic acid.
okay, but
Tim,
okay. Yep.
sorry, Raul, can you go to the slide where you put the plant size capacity, please? Because I remember you said that with everything that Gia brands produce of a gas, you were going to be producing lactic acid for the 0.5% of
Where,
Latin
sorry?
America in the plant capacity.
There?
Yes. Yes, over
Yeah.
there, you say the production capacity is almost 100,000 kilograms of lactic acid per year. So somewhere you disconnect the proposed plant capacity and when you scale up. Because yes, over here you have 38 batches per year and 99,000 kilograms of lactic acid.
Yeah. Also the yields that also is different.
Yeah, I'm sorry. The correct answer for the production capacity, it would be 61,500 kilograms of lactic acid per year using this wet bagasse.
Okay. Yeah, please correct that. Thank you, Mariana. And
Yes.
last question about, could you please put the prices, the equipment price, please? Okay, that where do you get these prices, guys?
We got these prices in Alibaba.
Okay, I think you
Okay.
need, yeah, you need to keep a double check because it's very, very cheap prices. I don't think that IVA is in Spanish also, but well, this doesn't matter. But yeah, check it because it's. I don't think so. It will be the prices here, and so the capacity of that of the equipment you need, even that. But also, I don't know if it's in the signature, but also need to consider the other things that auxiliary equipment and estimate. You can also Super Pro can estimate about it and estimate about the plant costs also. They have a algorithm here, then you can check it out.
Oh,
Yeah.
it's because we actually did use the Super Pro economic evaluation,
Okay.
but we modified it in order to decrease the prices because Super Pro, I don't know why, we had like we put in the unit operations the price of each equipment, and it like added a lot of costs that we didn't know what they meant. So we chose to use like some Super Pro information for reference, like how to calculate all that. And we also modified by ourselves the rest of the information. We have the link to each unit operation in case you wanted to see it. We can send it to you through the teachers.
Thank you. Thank you. Yeah. Please always check those only. Yeah, because nanofiltration, it's okay. But that's it. Thank you.
Thank you, Raul. Cesar, Emilio,
Sí.
any questions? And remember, team, everyone has to answer questions, please, not just Mariana.
Okay. Do you want to go, Emilio?
Sure. Okay, so you mentioned in the beginning that lactic acid can be produced up to a yield of 90 to 95% uh, weight percentage in a tank. How does that affect the growth of your microorganisms? And wouldn't it be more time efficient to do shorter um, fermentations that reach lower concentrations?
Actually, yeah, we were thinking of that, and maybe we will need like more trials for that because when we did the lab experiment, we of course we needed to optimize a lot of things, so we didn't have really um, accurate data. Well, not accurate, but it could be better. So in the literature, we saw that the longer the process was, mm, like around 3 to 5 days, the more you produce lactic acid, making some reference. But yeah, maybe if we made the process shorter, we could get a little bit more of biomass.
I mean, yeah, of course, like you're going to get more lactic acid the longer you leave the fermentation to go. But like, how long does it take to produce, for example, 60% of the lactic acid? Because if it takes like 10 days instead of 20 something, then wouldn't it be more cost effective to just run the fermentation for the short amount of time than for the 25 days that you have right now?
Sorry,
Yes.
can you reformulate the question, please?
So, when you did the research on the production kinetics for the lactic acid, um, like how many days approximately does it take for 60% of the lactic acid production to be reached? Because it's not linear, you know, and like everyone knows it's not linear. Uh, so wouldn't it be more cost effective to have a shorter fermentation with lower yield uh, if the production speed decreases as lactic acid concentration increases? Because I'm not sure that you showed the kinetics graph in your presentation.
Yes. Thank you, goal 3 point.
Sorry, I lost connection and got lost. Could you please repeat it?
So I was asking that if I'm not correct, if I'm correct, you didn't present the kinetics for the lactic acid production in your presentation, right? Um, so what I'm asking is, while you did your research, did you like how long does it take to, for example, produce 60% of the lactic acid uh in your goal? Like, wouldn't it be more cost effective to run the fermentation for a shorter amount of time instead of letting it go until the 90 or 95% production?
Maybe it could be more cost effective because at the second, third day, to the second, third day, I saw some references that achieve like more or less 60, 80% of like the highest. So maybe with shorter uh, fermentation processes.
Mhm.
But
Okay, thank you, Pamela. I would like to ask also, Javier, can you guys go to the slide with the cost of the equipment? So while you get there, I take that those costs that are there, they are in US dollars, right?
Yes, all of them.
So remember that if you are using US dollars, declare it early in the table, not at the end with the amortization. And if you're saying it both in English and for US dollars, don't use IPA, use BAT, which is the equivalent term. So it's easier for us to understand that. I mean, as Arun mentioned, you do have like a lot of expenses that you didn't really cover here. Uh, Oh, maybe think that those expenses that SuperPro showed you, you didn't take in account before. Those are the expenses for the secondary equipment, for the tubing, for the accessories required for each one of these equipments. And also, whenever you show the capital investment, maybe tell us not only the uh, process operation you are going to cover with the equipment, but what the equipment is. Because like I know that you need a tank for the blending tank, you need a tank for the storage tank. I need to know how big they are so that I can have a scale of, well, how if they're if the costs are adequate or not. Why didn't you consider the chromatography module, not the columns? Because the columns, they are not on the capital investment. They should be actually on manufacturing costs, indirect manufacturing costs.
Uh, you are asking why didn't add the chromatography or
The module, because it's not just the columns that you have to buy. Like the columns are just columns. They're not going to do anything if you just like connect them with tubing to your process. You have to have a module that controls the flow and pressure on the chromatography columns. Why didn't you include this cost?
Hmm. Actually, uh, we estimate the cost of the columns only in basis of the scale of them we done. Um, for the mold, and it should have okay. Obviously, for this operation process, we are going to take care of the conditions and everything. The okay, yeah, actually, all the conditions that need to be handled of this question, and uh, we thought that with the calculate that we done, it will be enough to take a to to make the escalation right.
I don't think you're getting the question. So because I understand that you scaled up your columns, etc. There's an equipment you need to put the columns into so it so the separation actually happens. Like it's not only the columns that you have to buy. You put the columns somewhere, and it's not just connecting them to tubing in your process. But okay. Uh, so what's the goal application for your product?
For using it in food industry.
Mhm. So I would like to uh, oh, I would like to ask Omar. So if it's an application for food industry, is it really needed? Do you really need to have an ion exchange chromatography for this application for the purity required for this industry?
Yes, it's necessary because we made in laboratory, and the exchange helps to remove the cations, particles that we are having, and in the change of the pH, we remove the little particles that we don't need for the purification in the lactic acid. So also in literature, it talks about they made in ion exchange for get a better results. Also, we can get until 98% of purification if we do all the steps correctly.
Okay. How much more time do you have? Sorry, I don't want to overstep my time.
We have time for Cesar to make the two questions.
Okay.
Thank you,
Okay,
Emilio.
go ahead, Cesar. Sorry, thank you.
Okay. I have a couple of questions, but I'm going to write in the comments in the forms. Um, but okay, is this what are you proposing is a new process, is a new technology? What about the intellectual property issues with this type of products process?
Well,
Uh,
it's not exactly a new process because we took like references from other bagasse, like yeah, carob bagasse, corn, sugar, purification, or production and purification of lactic acid. So mm, it was pretty much um,
Good.
available
Yeah.
to the public.
Do you know if there is any issues about the use of this technology regarding intellectual property? I mean, do you need to pay some uh, licensing of the technology, of the product, of any of
Mm,
these kind of issues?
Yes,
mm,
we will have to pay the patent in order to well protect our information for all the information and all data we got from through laboratory practices, experiments, through the investigation. We did consider that cost in the rest of the investment, not in the capital one, but in another section.
Okay. Um, the other questions.
Mhm.
Um, what are the main difference between the impurity of lactic acid bacteria and engineering E. coli? Since you mentioned that you select the lactic acid bacteria because in E. coli you have more, you mentioned contaminants. I don't know, how do you describe the disadvantage? of the hazardous impurities. Yeah. What the difference between the impurities between these two species? Since you are going to use a ionic chromatography, so based on that, what are the main difference and why you can use this E. coli?
Well, one of the reasons was like the E. coli has to get a genetic modification conforming the literature, and most of them require like change most part of the process and add more modifications. And then from the lactic acid is more, well, it could say is more easy to removal without genetic modification, have also easy steps in the ion exchange instead of the E. coli.
But I mean, you're going to use ionic chromatography, so
But the E. coli has like a tolerance in the acid conditions, and also you have to modify, so it will be more root cause to each step, and it also has to. I don't know if I say it correctly, but I think so. If is what do you want, like the question about? I'm not sure 100%.
okay. And last question: do you consider the cleaning time in your process?
Yes.
Okay, perfect. I didn't see the gun, so
No, it's in the actually it's in the fermentation. There is a cleaning process and a sterilization process. It's
yeah,
the
but the cleaning of all the equipment between
oh,
batches, did you consider this time in all your process?
no, we asked one of the doctors and they said it was not necessary to use the cleaning process to all the operations because it will be practically the same. The one that was important was the fermentation one because of all the impurities, like the how can I say it? The previous process would leave, and that's why we only consider the fermenter one. But in case
Mariana, you consider you can if you put your Gantt diagram, you will see you have discharge this time, and also we talk about regenerating the ion exchange columns, all the time of cleaning, of washing, regeneration. We talk about that. No, but here
You
you only
consider
have
that you have a sterilization in place.
yes, but only in the fermenter. That's what I was saying.
and then in the ion exchange columns, I don't know if you can put the Gantt diagram over there. Elute regenerate, that's part of cleaning before the next process.
Okay, thank you.
Okay, no more questions.
Okay, thank you very much. Team 1, team 2, I think Angela is going to be sharing the screen.
Thank you.
Thank you, teachers.
Thank you.
Thank you.
Please, team 1, don't go. Stay here until team 2 has present, please. And team 2, the same as team 1, we're gonna have 15 minutes to present, and then between 15 and 20 minutes of questions. Whenever you are ready, you can start.
Hey, good morning. We are Team 2 and we are going to present the economic and sustainability evaluation of lactic acid production and purification from stevia bagasse using Lactobacillus plantarum. Our team is Dorothea Renner, Mikel Seeger, Angela Martinez, and me, Joseph Tinoco.
So GeoBrains is our industrial partner producing 1.5 tons of stevia bagasse per hour. We aim to produce food-grade lactic acid with 88% purity through Lactobacillus plantarium fermentation. This project proposal is a multiple approach strategy with innovative biomass use that guarantees a profitable economic impact. So by using stevia bagasse, we introduced a new carbon source for lactic acid production. At the same time, it removes the bagasse waste from the environment. By combining hydrolysis, fermentation, and purification, we create an efficient workflow. This process is designed to be resource efficient, with focus on reducing water use and treating residues properly. Moreover, it has economic potential. The use of that local abundant biomass leads to a cost-effective production since we reduce the costs for raw materials. In addition, the process is sustainable because it supports a circular economy. So next we have a rough production description, a product description. As already mentioned, we aim for a purity level of 88%. Lactic acid has diverse uses, for example, in cosmetics as a pH neutralizer, in food as preservative and flavoring agent, and it's used in bioplastics. The global lactic acid market was valued at $1.6 billion in 2023, with a projected growth of 12.4% annual through 2028. By using all available stevia bagasse, Gia brands could cover 0.09% of the total market share of the target market, which is Latin America and the US. As you can see in this graph, by 2030, the market size is expected to reach $2.66 billion, growing at about 7% per year.
Now, for the available technologies we identified for this project, we have investigated about some of them. For the pretreatment, these are the ones we chose, which are in bold, and they are steam explosion, which we chose due to its relatively low capital investment, the ability to use high moisture content biomass, and the enzymatic hydrolysis since it enables targeted biomass breakdown. For separation, we investigated monopolar electrodialysis, but we decided against it due to its high capital and maintenance costs and membrane fouling. And we went with centrifugation due to the low cost and readily available technology. For purification, we chose ion exchange chromatography due to its efficiency and the selective removal of cationic and anionic impurities, and also rotary vacuum filtration because of its continuous operation, and it preserves lactic acid quality and meets the food grade standards relevant to our project. And finally, for concentrating, we chose vacuum evaporation, which is effective for concentrating the lactic acid and is energy efficient. But we also saw freeze drying, but we decided against it since it is not easily scalable, has high energy consumption, and is still an emerging technology. Sorry. For the properties of lactic acid, we're just going to mention that its pKa, it's 3.86, and it is highly soluble in water. Now we have our general process diagram, and here we can just see the operating conditions for all of the unit processes. The first row is from the pretreatment up to the fermentation part. And then in the second row, we have the downstream process, which I'm going to go into more detail here. Starting with the pretreatment process, we start with the 1.5 tons of stevia bagasse, and we add water to it. We create this water bagasse mixture. We take that to the steam explosion hydrolysis and then enzymatic hydrolysis, which would be performed with the hemicellulase as the enzyme. And then we have the first rotary vacuum filter. Then we have a mixer where we add peptone and yeast extract to addition the media. Then we have the fermentation after the sterilization in place, and we obtain this fermented broth after 36 hours, which we take here to the first step, which is centrifugation. Then we have the second rotary vacuum filtration, and then we're going to take that to the cation exchange and the anion exchange. And finally, we have the vacuum evaporation, which would concentrate our final product, and we would obtain the lactic acid.
This is a purification table for our process. As can be seen, we have a general 81% recovery percent and an estimated purity of 87%, which is like well within the the reaches of its intended use in the food industry. So yeah, like as shown, the chromatographies are the unit operations where we have like the lowest recoveries. So yeah, the next one. This would be the proposed bioreactor for the enzymatic bagasse pre-treatment. It would have a nominal volume of 86 cubic meters and a working volume of 60 cubic meters, and the process duration would be 24 hours for this hydrolysis. To save up on enzymes, we could like immobilize them on calcium alginate carriers, and in this way, like according to the paper seen on the quote seen on screen, like we could save up to 60% on enzyme costs compared to free enzyme utilization. For the bioreactor, we would have a roasting impeller, and for the construction materials, we would have stainless steel 316L for the wet parts and stainless steel 304 for the non-wet parts. And this because this 316 steel has a higher molybdenum content, making it more anti-corrosive than the other one. It would have a agitation speed of 23.7 rotations per minute, a pH of 7, and a temperature 55 degrees Celsius, and a 24-hour process time.
So for the first filtration we have in this system, we're going to use the Kraus-Maffei vacuum drum filter. We're going to have work for a particle size of 250 micrometers, filtration capacity and throughput and filter area can see down here, and with the speed of 3000 RPM. This is going to be the first step in our filtration. There are going to be later steps, but this is mainly to remove all the solids that we have not been able to break down into glucose before our fermentation.
For the fermentation, we would have the following bioreactor. It would have a nominal volume of 74 cubic meters and a working volume of 52 cubic meters. It would have a process duration of 36 hours. This based on literature, where like the highest yields of lactic acid were at 72 hours, but at 36 hours, most of the lactic acid was already produced. Likewise, it would have a roasting impeller, and the construction materials would be stainless steel 316L and stainless steel 304. It would have an agitation speed of 17.85 rotations per minute and an initial pH of 5 to 6, which would go down to around around 4 by the end of the process, and it would have a temperature of 34 degrees Celsius, ideal for our bacteria, and a process time of 36 hours.
As next steps, we have the centrifugation. We're going to use an alpha level Aldec G3-105 decanter centrifuge for efficient solid removal. This is the first step in our removal of the solids. It's going to have a rotation force of 2,700 Gs. The length and the width is also seen at 4.5 and 0.9 meters, and the sigma value. This you can see the lab scale, and then you can see the industrial scale on the higher picture. The next step in removing the solids before we go into more deep cleaning is the filtration. Here we will again use the Kraus-Maffei vacuum drum filter, but we will use another particle size for our filter, at this point 1 micrometer. The filtration capacity throughput is the same, but the filter area and the sizing of the drum filter has changed. Also, the speed will be lower to ensure optimal size of the cake to ensure efficiency in the process. After our filtration, we'll go to the cation exchange. Here we'll have 3 columns to distribute the input flow. We're going to use the Cephadec CM Hyper D resin. It's a weak cation exchange resin. The flow rate per column is going to be 29.2 liters per minute. The service flow rate will be 9 BV per hour. The regeneration flow rate will be 4 BV per hour. The operating pH range is going to be 2 to 7 compared to when we use the regeneration, flash, wash, and loading phase. And the operating temperature will be 25 degrees. Looking at the anion exchange, we're going to have right after, we're going to use the Amberchrome 1X4 resin. It's a strong base anion exchange resin. Here we're also going to have 3 columns at the same sizing, but the flow rate will be different at 28.7. The surface flow rate will be 9 BV per hour. The regeneration phase will be slightly higher at 4.2, and the operating pH range will be more strict from between 5 to 7 pH, with the operating temperature again at 25 degrees. After anion exchange, we'll come into the concentration. Here will be vacuum evaporation with the STK Machina vacuum evaporator. We're going to have two with 5,000 liters capacity each, as our total input flow at this point will be 8,154 liters per hour. This will, of course, change depending on how efficient these chromatography will be, which will depend on the individual fermentations as there will be change. To ensure optimal usement, we're going to have storage tanks in our system. We're going to have two different storage tanks, one after pre-treatment and one after fermentation. Pre-treatment is going to be 54 cubic meters, and after fermentation is going to be 52. And construction materials here will be stainless steel, either 304 or 316. Yes.
Here are the key international standards and regulations related to food safety and production. First, we have Codex Alimentarius, which sets purity criteria for food additives and establishes approved usage limits. The GMP ensures clean, controlled conditions and the use of safe raw materials. Next, HACCP focuses on risk identification, such as microbial contamination, and emphasizes regular testing and monitoring to ensure safety throughout production. In the US, Title 21 CFR specifies permitted production methods like fermentation and requires compliance with Food Chemicals Codex purity standards. The FSMA aims to prevent contamination and enforces safety risk management. On a global level, ISO 22000 sets food safety management standards ensuring traceability throughout the food supply chain. In Latin America, Central American technical regulations are aligned with Codex, ensuring regional consistency with international standards.
As for the waste management and their disposal, these are the wastes that will be generated from the process. Mainly, we have the water from the vacuum evaporator. This water we could recirculate it back to the process, and then we have the hydrolyzed bagasse residue after the enzymatic pretreatment, which would be generated at a rate of 2,450 kilograms per hour, which would have a water content of 40%. We could dewater this residue and return this water to the process, and the rest we could have several uses like making feedstock or making it fertilizer, as long as it doesn't contain heavy metals or hazardous waste. For the centrifugation solids, we would have a 72 kilograms per hour. And for the filtration solids, we would have 144.63 kilograms per hour, which we could also make feedstock or fertilizer, as any bacterial residues are not so hazardous because the lactic acid bacteria are non-pathogenic. And lastly, we would have acidified water from the chromatography columns, which we could dewater and recirculate as well, and the rest treated as an acidic waste. And we would have also the regeneration fluids for the chromatographic resins, which we could since they are solvents, regular solvents like alcohol and acids, we could just evaporate them and return them to a process.
Here's the key steps and their risk in our process. So first, the bagasse pretreatment. The main risks here are enzyme denaturation and incomplete hydrolysis. To control these, we monitor particle size, pH, and temperature using online probes. For centrifugation, the risk is incomplete separation. We control this by maintaining the RPM and the flow rate monitored with flow sensors. In rotary vacuum filtration, membrane falling and contamination can occur. We address this with regular cleaning and pressure monitoring. During fermentation, the risks are contamination and pure yield. We ensure sterile conditions and monitor pH, temperature, sugar concentration, and lactic acid using HPLC. For ion exchange and evaporation, risks like resin inefficiency and product degradation are managed by optimizing pressure, temperature, and monitoring regeneration cycles. We measure lactic acid concentration and purity using a refractometer.
Perfect. Yes, then we have the Gantt diagram right here. As you can see, each single step, and our main that we have that takes time is our reaction and the fermentation, as you can see in the Gantt diagram here. For the next one, we have the economic revolution. We have the executive summary of our whole process, and it's going to take 4 years for our product to be profitable. And we have the annual operating time, where we will have 240 batches a year, and our average batch time is 59 hours. Yep. Next one.
And finally, for the funding sources, we could use the stock market initial public offering, which would be when GA Brands goes public and starts selling shares in stock market, or using company bonds, since they avoid equity dilution and they have fixed interest payments. And that's the last one. Thank you.
Thank you very much.
Thank you, Team 2. Any questions, Raúl, Emilio, Benjamin, Cesar, for Team 2? Or any individual ones?
Yeah, I have questions. Let me, I turn off the camera because the internet. Can you put the column process section, please? Here, that a quick question, just only. What is the material of the holding column?
That's going to be stainless steel.
Stainless steel. And what do you will use for regeneration and?
For regeneration, it depends on each one. We put them in here in the downstream process, where we'll be using mainly HCl and water. And then for the regeneration specific, it is sodium hydroxide. And let me see, I have it here. The first one will be sodium hydroxide and water for the cation. And for the anion, we will be using HCl, sodium hydroxide, and water.
And the question is, are you sure that the stainless steel doesn't get corroded by HCl 3%?
At the constant. Oh yeah, sorry.
Yeah, like the stainless steel varieties would be like the 316L or the stainless steel 904. Like both of them have like the molybdenum content that I mentioned, which makes them anti-corrosive, and the 904 variety has like a higher nickel content that has a higher nickel content of the two, so it makes it more resistant and less prone to corrosion.
Okay, good question. Good answer. Thank you. Other question that in the HACCP, could you please the slide of the hazard analysis? I see here there is some risks that are not directly related with a hazard analysis. So it's more related that production risks or efficiency risks. So you need to take into account that here is more like a health risk, something like that.
Like this is more focused on the quality of the product, like to ensure that we have that quality that we were promising with the 88% purity, and also that it doesn't get damaged, which is also part of
yeah, but it mainly is for just taking kind of there is some kind of risk that. Okay, and the other one it's about the management of the waste. I hear that. Can you explain how do you manage the waste? Can you tell more about it?
So like there are multiple ways in our process right now. We set up in Pro. We are mainly paying other people for dealing with our waste. It is actually quite a high profit, quite a high expense on our part. Of course, the water can be reused But like separating HCl from water in our regeneration and sodium hydroxide is probably not going to be profitable compared to just like paying people to get it off our hands from what we researched. So like the water we can use centrifugation solids, as long as they're yeast and biomass, most of it can be composted. And also the same with our filtration solids. But as soon as we start adding acid to it, we are mainly just paying people to get it off our hands, as like the recovery process is not worth it from our research.
Okay. Thank you. That's all. You are mute, Beatriz.
Thank you, Raúl. Emilio, Cesar, Benjamin, I don't know who wants to go next.
Actually, I have the same question that Raúl regarding to HACCP and the waste management, so I will pass. Very good job.
Thank you, Cesar.
Okay, can I be the one asking something to these young fellas?
Go ahead.
Yes, Benjamin, go.
Okay, I have several doubts, okay, or questions. Why? I guess you're lucky you have you're part of a faculty with a lot of doctors that have an extensive experience in processing, and we can understand what you were trying to achieve with this project, particularly in the pretreatment and bioreactor sections of your project. Why? Because I have, I want to ask you, you didn't mention it, but are you taking into consideration the composition of the bagasse? Because I'm seeing that you are proposing a steam explosion, and then you are going to remove the solids and then add a protein source. So that do you know which is the protein composition of the stevia bagasse, or you are just assuming that it's a low protein one?
We do have the technical sheet of the composition of the stevia bagasse that the training partner provided, and that's where we got the information for like the lignin content and the fiber content. That's the percentage. We have that in the report, not here, but that's how we chose the steam explosion and enzymatic hydrolysis because it was suitable for the stevia bagasse.
Yeah, but can you please tell me the composition?
The composition?
Yeah, how
Well, I
much
have the
cellulose and hemicellulose and lignin is present on your bagasse?
Yes, I have it in the report. If you could give me 1 second, but it was around 40% of the 1 second.
Well, the question is because it's not just that you need to know the composition, but you are expecting to use a steam explosion without any acid or alkaline compound. Yeah, is that right?
Yes, it's just the steam.
And you are hoping that with just water and temperature and pressure, you are going to have what kind of yield of conversion from cellulose to glucose without any or less inhibitors?
So that's why we paired the steam explosion with the enzymatic hydrolysis because just one or the other was not enough because we performed this in the lab in the first course. So that's why we paired the steam explosion and enzymatic that yielded the highest amount of glucose. Because I have the information now, the soluble fibers was like 4% of the stevia bagasse, and the insoluble was like 54%. So after these two, like the combination of these two hydrolyses, we could get the highest yield of the soluble fiber.
Okay, but you're aiming for glucose.
Well, yeah, the glucose. We measured the glucose content. Yes.
So why are you using an hemicellulose enzyme?
because the bagasse has a high content of like the lignocellulosic. It's a lignocellulosic source. So
Okay.
this way we can break down the stuff.
Yeah, but cellulose, hemicellulose, and lignin are mainly the the main composition of any vegetable bagasse, no? Okay, but which is the I'm asking you, the hemicellulose, which is the carbohydrate composition of hemicellulose?
I don't have that information right now, sorry.
Okay, hemicellulose is not mainly composed by glucose. It's mainly composed by galactose, hylose, and araminose. It depends on the source or vegetable source, but cellulose, it's the main polymer that it's composed mainly about, mainly of glucose. So that's why I'm asking. It's because maybe you need to use an enzymatic cocktail that can assure you that you're going to have more glucose, maybe a cellulase, and a hylanase present in the mix.
We did have that in the first cycle we did where we were breaking down. We had a cocktail, especially to like work with this. We also did an acid treatment, but it was the enzymatic that had the least issues coming forth. But yeah, it was we had three different enzymes: one for the cellulose, one for the galactose, and one for the glucose in the
Okay.
hemicellulose.
Okay, and why did you discard the glucose and the glucose enzyme?
One more time.
Why did you discard it? Well, why did you didn't select the cellulose one instead of the hemicellulose enzyme?
Let me see. Is it specific to? Yeah. Well, that just had to be added that it's going to be a general cocktail. In our Super Pro decision, there is just a general enzyme cocktail that has been added, not the specific enzyme written down.
Okay, and another and last one question for me. In the fermentation step, you told us that you are using a fermentation time that has been reported previously on literature. I mean, I thought you said the
Both literature
36
and
hours.
laboratory experience.
Okay, the problem here is that I wish that you had made a maybe a simulation using a model, okay, for you to make a kinetic assessment of the time, okay. So did you did that? Did you use a uh, how can you say that? Maybe Monod model um, to simulate the consumption of glucose and the biomass and lactic acid production.
We
With
have the general mass balance, but what you're asking for is part of our other evidence. So it was not used for this. It's going to be part of
Yeah,
our
I know, but
evidence
I
one.
mean, if
So
you did the work, you might be able to uh, to answer my question because what I was expecting to see is that based on on your modeling, you could make an educated guess about the processing time that will be required on the fermentation. Okay, so if it's a batch reaction, well, you just need to set the time or see the time or determine the time when the substrate it's going to be consumed fully by the bacteria. Okay, so that's the what I was expecting to see, not just a reference about previous experiments. You might be able to how you say this? You might be able to compare those times in the literature to your modeling experiment or your modeling exercise. Okay, so that's that was my first one of my doubts. Okay, but that's all for me. I don't know if someone else. want
Thank
to.
you, Benjamin. Emilio, any questions for team two?
Yes. Actually, you can stay here on this slide. I would have liked to see at least the uh masses for the flows here, because we have the processing conditions, but we don't have the masses. But I would like to ask, like, who was who was the main designer for the filtration operation?
The one after the fermentation?
Yeah, the rotary filtrations.
That's me.
Okay. And who was the main designer for the chromatographic operations?
Yeah, it was like a mix of like parameters we said from literature and from the Super Pro and from lab data.
Okay, but who did the most like work for
In
scaling up?
Super or just in general?
Like in general for the chromatography. Like, who knows the most about the chromatography out of you four?
Like if there's questions to it, I would gladly answer it, but it was not only me working on it. It was like the chromatography was a joint effort.
No, because my point is actually that I want to ask to someone who wasn't that involved to see how much they know. So I would like to ask, for example, Angela, um, do you think the filtration operations you decided are feasible on the scale you're working with?
The rotary vacuum ones,
Yes.
if they are feasible.
Yes.
Well, according to the scaling, it is feasible. Like the equipment seems to suit the scale of the project. So I would say so.
Because these are like huge drums, like 52 square meters and 40 something square meters of membrane area in the drums. And it's a relatively high RPM for something that should be like, what's the diameter of the drums?
Can I add something? Like when we looked for the equipment, it's actually one of the smallest modules from that company that it's providing. So there's much bigger rotary drum filtrators.
Okay, so can they operate at that speed? That's just a question.
Yes, like we have all the data from that company
Okay.
producer actually. So
Okay,
what they can
good.
offer.
Yeah, thanks. So about the chromatography, can you go to your purification table? So, like, it seems to me kind of low purity increase for the chromatographic processes. Like, do you think that the I would like to ask, maybe already Angela has answered or he answered, maybe Jose, um, do you think that these chromatographic processes are feasible, or more like, are they worth the cost for increasing just that purity percentage?
Mm, And yes, well, like the first caveat on those purities is literature. Like we didn't measure like it from like lab data, so like and I remember that some of the papers we used where we found like those purity fold increases, like they had some like some other operations like monopolar dialysis or like something like that that had like array purified, so like maybe the jump would be higher in reality. Um, but yeah, like the anionic definitely is worth the price because like it traps the lactic acid. Like the lactic acid solution goes like at a pH 5, um, where the lactic acid would be like in a negative, that would have like a negative charge, so it would bind to the resin, and the elution would be at pH 2, where it is the lactic acid has a neutral charge. So like it would bind really effectively to the lactic acid, and that what would definitely be worth the cost.
Okay. So just to finish up, in this chromatographic processes, Mikhail, what are the contaminants you guys are eliminating? And according to those contaminants, would they be relevant to eliminate, or would it be more cost effective to just stick to the rotary vacuum filtrations and then the vacuum evaporation, then just call it a day?
There's definitely an argument for calling it a day there because we have quite a high amount of lactic acid already after there as we remove the solids. But we will still have like rest of enzymes from the earlier production. We will have like other byproducts made by the yeast that will have to be removed, especially not by the yeast, but lactobacillus. And especially when we look into like what acid is food grade, we have to be notified. Of course, it has to be 88 purity, but there's also other stuff in it that you don't want to have a high amount of.
Like
For
what?
example, the enzyme we have used and like the other acetic acids that has been produced. And this is the main way we remove them. Especially if you look at our waste streams, that is like, it is also our most efficient step for ensuring that there's no rest of the bagasse, digested bagasse, any glucose, anything like that. So yes, it is an expensive step, but it seems like a necessary step if you look at like our general streams and what is removed in the ion exchanges.
Okay. Thank you. That will be all for me.
Okay, if there is not any more questions, I think we finished. Thank you, team two. And thank you, Emilio, Cesar, Benjamin, and Raul for being here today. Raul, we're going to send you the presentations and also the final report to you, to your email. And I don't know if Emilio, Cesar, Benjamin, Raul wants to say anything before you go.
No, it's a good job, guys. Thank you very much. Very good work. That's it.
Nice job. Congrats.
Nice job.
Thank you, everyone.
Thank you.
Thank you for being here.
Thank you. Thank you.
Yeah, thank you, guys.
So please, team one and team two, stay here.
Okay. So, see ya.
Bye,
Thank you.
Benjamin. Bye.